even though people seem to be still digesting their food. So, but we'll start. So welcome back for the second session today. I don't have to tell you about the importance of the Simons Institute and things like that right now, but I want to welcome Etienne Pardoux, who is well known to have sort of studied functional limit theorems and things where we don't just have the differential equation, but PDEs or differential equations. And if you want to know anything about this mathematically rigorous, Etienne is certainly maybe one of the people, but probably the person to talk about. So I'm looking forward to your talk.
Thank you very much. Thanks for the organizers to invite me to this, for inviting me to this very nice workshop and giving me the opportunity to present my work. So this is joint work with Guo Dongpeng, and it's about functional law of large numbers and PDEs for spatial epidemic model with infection age-dependent infectivity. And the spatial could be thought maybe as graphon if you prefer. Okay, you will see. Okay, so let me first explain the spatial model. So we consider a population of fixed size distributed in k locations, x1, xk. And for simplicity, I say those locations are in the interval 0, 1, but it could be generalized. And let I and k be a partition, k from 1 to capital K, be a partition of 0, 1, such that the interval I and k contains a point xk. Well, I don't know. Sometimes I probably the n should not be there, but of course all these depend upon n, as you will see. And for simplicity, I assume that the length of each interval is exactly 1 over k. Now, the individuals do not move between the locations. Okay, I have another work where I study almost the same model, but where there is movement, it's more complicated. Okay, here there is no movement between locations. So it's really like a graph model and in the limit graphon model. So there are B and K individuals in each location, and the sum of the B and Ks are exactly capital N. Okay, so in each location, individuals are characterized into 3 groups, S, I, and R. So it's an SIR model. There is no loss of immunity, like what we have seen earlier today. Okay, so S like susceptible, I like infected. I will discuss infected or infectious in a minute, and R like removed or recovered. So we denote the number of individuals in those compartments at time t and location xk as Snk of t, Ink of t, Rnk of t. And for all t, of course, the sum of those 3 guys for each k is exactly b and k because there is no movement. Okay. So now we define piecewise constant functions of x. Okay, so instead of talking of Snk of t, I prefer to talk of Sn of tx, which is that just a function which is constant on the interval I and k, constant equals to Snk of t on the interval I and k. The same with I and R. Okay, so I want to think as those quantities as indexed by t and x. Okay, so in each location there are 2 types of, there are 3 types of individuals, 3 compartments. But now let me discuss another point, which is at time 0, there are those who have been who are infected at time 0. Those have been infected in the past. Okay, so and there are I and k of 0 of those. Okay, and all the others, and they have been infected in the past, and those who are susceptible at time t. Okay, they may be removed or recovered in years at time 0, but we don't need to talk about them, and they don't really play a role in the epidemic. Okay, so those who are infected at time 0, they have been infected in the past. So those, okay, they are the index minus j is because, so for infections after time 0, there is the index are 1, 2, etc. J is positive, and for the infection times of those who are infected at time 0, it is before, it is with minus j, and this is negative quantity. Okay, this is a time at which the individual j has been infected in the past, and he's supposed to be still infected at time 0. If not, it would be, of course, in the R compartment. Okay, and those who are susceptible and may or may not get infected later. So get infected means jump from the S compartment to the I compartment at time. Okay, now here, this index is an index for individuals. Those individuals, we know how many there are. And those indices are for, this is the first time of infection of one individual. This is the second time of infection, another individual, etc. Okay, the numbering is according to the increasing sequence of infection times after time 0.
So I have 2 clarifying questions.
Yes.
Tau minus J are not all over time.
No, they could, well, they could, but
you don't care. Oh, they're not over time.
Well, they are, well,
you didn't write small.
It's not, yes, it's not important to order them, but you can think they are ordered. In a minute, a bit later, I will talk about the point measure which with Dirac mass at those points. Okay, but okay, whether they are ordered or not, it's not important in my term.
Yes. Do you have any removed or recovered at time 0?
They could be.
Okay,
but
so it's not yet.
It could be,
but typically the number of susceptible is BK minus IK of 0. Is that correct?
The number of susceptible,
No, because he may have recovered.
they may be recovered. So,
I thought you said there were no recovered.
But if they're recovered, but if they're recovered, you can just take them out, right?
Yeah. Yes and yes or no, because when you compute the probability that the guy you meet is susceptible, you divide by the total number of people in the patch, in the compartment, in the patch, and then the removed clear.
And should I think of in each patch, I have infinitely many patches, and in every patch there are infinitely many people?
So, oh, okay, you will see. Yes, in a sense, yes, but you will see. For the moment, it's finite. Your being is finite. Okay, so now for each J and K, so K is for the patch, J for the specific individual. So K is between 1 and capital K, and J is either a negative number for those who have been infected before time 0 or a positive integer. And so J runs in Z, but there is no J equals 0. Okay, so those functions, lambda JK, this is an IID collection of random elements of D of R with R plus. So D is a scored space. If you like, you can say C, they could be continuous, but because I want to include the more classical models where lambda is 0 and then jumps to a fixed value and then jumps back to 0, I prefer not to restrict those to be continuous functions. Okay, so they are just right continuous with left limits at each point. So this is a scored space. Okay, and they satisfy lambda of t equals 0 for all negative t. Okay, and okay, so let me draw a picture. So, okay, so this is the time of infection. So, after the time of infection, there is possibly an exposed period during which lambda is 0. Okay, you are not infectious when you are exposed. Okay, you are infected but not infectious. But I don't separate the compartments E and I. I could. It would just add another equation. It would complicate. I don't think it's very useful, but I could do it. And then presumably I think of lambda to rise rather quickly to a maximum. Okay, for instance, apparently, in the case of COVID, this maximum should be shortly before the symptoms outbreak. Okay, and then you think that this decreases more or less quickly, and then hits 0, and then it's 0 forever. Okay, so those functions lambda, they are random functions which are IID, and I think of those to be roughly of that form. But if you prefer to have a jump to a fixed value, and then it's possible also. Or they could, they could have jumps and then, okay. So, and of course, okay, in here, of course, t equals 0 is the infection time. Okay, so infection time is 0 for this, and so lambda be 0 for negative t is just before the infection of time. The infection time, of course, lambda is 0. Okay, and then one important quantity is the duration of the infected period. I don't say infectious because I include E, okay, E plus I, if you like. I include the, okay, so this is here, this is, okay, this is the lambda and this is the eta. The durations, the time, from the time of infection, the time it takes for the lambda to hit 0 and remain 0 forever after that. Okay, so it's the last time that lambda is strictly positive. Okay, so at time tau n jk plus eta jk is the individual j jumps from the I to the R compartment.
Is probability 1 as mean as anything, or you should ask?
Good question. I'm not sure what I need. I'm not sure I need to assume anything for the talk I'm giving today. Okay, usually, okay, by the way, one important thing is R0. What is R0 in this model? R0 is the expectation of integral from 0 to infinity of lambda of t dt, which, okay, later I will write lambda bar of t for the expectation of lambda of t. So it's just the integral from 0 to infinity of lambda bar of t dt. Okay, so now usually you expect R0 to be finite. Okay. I mean, for most diseases, it's more reasonable. and I expect eta to be finite almost surely, but whether it's, I'm not sure it's really important in my case. Yes.
The index j and k, are they related to this location, or is it just two arbitrary individuals?
No, k is related to location, of course. K is a location, and j refers to different individuals, distinct individuals.
But, so R naught is then independent of the location?
Oh, because they are IID, so the same law. So it doesn't depend. Okay, I should write it lambda jk, but then the expectation doesn't depend on jk. By the way,
so this means that
yes,
there is no space. You infect all regions at equal rate.
No, wait a minute. I have not described what you are discussing, something which I have not yet described. Okay. So by the way, there is a question whether the law said certainly you want the lambda jk to be IID when you vary j. Should they have the same law for all k? I mean, it's the same disease, but maybe the climate is different. So should the law be dependent upon k? So here the law is not dependent upon k. But then, okay, when I was preparing this talk, then a couple of days ago, I sent an email to my co-author and I said, well, why don't we take the law of this depend upon k? He said, well, I suggested this 6 months ago and you said you don't want it. So. No, first I thought, let's start with something rather simple, but then I thought, why not? Okay, maybe, okay, that's another question.
So
okay.
If it depended on k, would R not be an average over k? Or?
No, okay. R naught would depend upon k. Then, okay, then if you, okay, then how you define R naught is a fixed parameter? I don't know. Okay, that's another question I don't want to discuss because I'm not. Okay, so now something very important is the total force of infection in the population. I mean, in the total force of infection at time t in location xk. Okay, of course, usually the total force of infection is just lambda times lambda beta, whatever you like to call it, times the number of infected individuals. Okay, but here, because infection, it depends upon the time since the age of infection of each individual. So the total force of infection in the population is something much more complicated. Okay, so you have first the total force of infection at time t of those who were already infected at time 0. This is the quantity. Of course, those are negative, so it's t plus something. Okay, the age of infection for those who were already infected at time 0 is larger than t, and this is the age of infection of those who were infected after time 0. Okay, where an of t is the number of initially susceptible who have been infected on the interval 0t. In fact, I could have put here S and K of 0 because of my convention that lambda is 0 for negative argument. Okay, I could sum over all everybody. I mean, all who get possibly infected sometime after 0. Okay.
But your first thing now might come into because the lambda of t minus tau could be 0 at time 0, or the lambda is always 0. Okay, no, it doesn't. So
It cannot be 0 at time 0. It's 0 at negative time.
So here you only have infection within. There's only infections within each location here.
No. Wait a minute. Next slide. You're too fast. I mean, I'm sorry. I need to. I guess I need to explain step by step. For the now, this is only the force of infection at each site.
Yeah, from within. Yeah.
Within each site. Okay. So next we will see how the epidemic propagates. Okay. So and then again, as for S, I, and R, I define Fn of Tx to be the piecewise constant function of x, which defined from those quantities. Okay. Now comes what Tom wanted me to explain at very first. Okay, let P denote Pk be denote mutually independent. Oops. Oh, that's correct. Let Pk denote mutually independent standard Poisson processes, so weight 1 Poisson processes. Usually, I don't like to use time change Poisson processes. I prefer to use integral with respect to Poisson model measure on R2 plus, but I know that some people are not used to that, so I use a simpler. I mean, for the proof, it's simpler. It's much more technically, it's much more convenient to use space-time Poisson model measures, but for the exposition, it is equivalent. So let me do it like this. So the number of people who have been infected between 0 and t in the location k, this is a Poisson process, time change by this integral, where epsilon n k of t is, okay, so you see there is infection from all the other sites. Okay, so you take the force of infection in the site k prime, you multiply by the coefficient beta n k prime, you sum over k prime, there is this normalizing constant, which is the length of the intervals, and then you multiply by the probability that the person you encounter in the patch k is susceptible. Okay, the proportion of susceptible at time t in the patch k, xk or whatever. Okay, so this is the rate at which the epidemic propagates in patch k. Okay.
sorry,
That's a
Beta n k prime is this is a matrix of positive coefficients or non-negative. Some of them could be 0. Maybe you never infect from very far away. Maybe you only infect from neighboring sites. I don't know. Or maybe it's a graph and you infect along some of the edges of the graph, not all edges. So this need not be those coefficients need not be all positive. Some of them can be 0. But this tells you roughly at which rate the infection from K prime to K.
Yeah, that's the spatial structure, as I'm saying.
It's the spatial or graph structure. Yes.
So is it correct to say it kind of has like a reaction diffusion feeling, because within the patch there's the dynamic identified, and then this is kind of just like this is the flow within K from all its neighbors, and it kind of alternates. I guess I mean like this flow is not really based on contacts bumping into each other per se. It's really just by neighborhood structure of a graph of K patches.
Why it's in contact? Maybe okay. For instance, okay. Suppose you live somewhere and every day you move to another place for work, or maybe on weekends or vacation you go to visit your family, or you go for vacation in some place, and you are infected, and maybe you infect people in this other place while you are visiting. But you are visiting and then you come back home. So I have no idea how to model these movements of going somewhere and coming back home by a usual, movement model of movement. So I prefer to say this is infection at distance. Although it's not really distance.
It's Lagrangian mobility. You can use Lagrangian. Yeah, that's temporary movement. You go and come back. So not
okay. Maybe I have to learn about that. We can talk about that later. Okay, so that's it. And finally, now we want to do a little more. This will be for the PDE part of the talk at the very end. So we want to define the number of infected individuals at location xk and time t who have been infected for a duration less than a. Okay, this is the age of infection. Okay, so you take all the initially infected individuals whose age of infection is less than a. So if you like, t minus this is less than a, and then all those who have been infected between time 0 and time t with age of infection less than a. So this means that you sum the summation at this point at a n k of t minus a plus 1. Okay, and then again this function now of 2 parameters ta becomes a function of 3 parameters when I consider this as a piecewise constant function of x. Okay. Okay, so now the stochastic finite population model. So we have SIR, so Sn of Tx is Sn of 0x minus, oops, very sorry, this is A. This should be An of Tx, okay? Those who have been infected between time 0 and time t. Okay, so maybe I write it here. So the correction of the wrong formula is Sn of Tx is Sn of 0x minus An of Tx. Okay, and then the infected ones, those who were infected at time 0 but are still infected at time t, because that sum is larger than t. And similarly, those who have been infected between time 0 and time t, and who are still infected at time t. And then the recovered ones, so you may have recovered at time 0, plus those who were infected but were infected at time 0 and are already recovered, and those who have been infected between time 0 and time t, and who are already recovered. X is
It's a patch, right?
yes, okay, I should, yes, you're right. I have changed. So in the second and third identity, what is what is, okay. Anything which is indexed by k, we should have a sum over k. So let's say ak times indicator function of I k of x. Okay. So I don't know, maybe I should have kept the notation with k. Okay, so, and now any quantity, of course, this is a model, but as we will see later, the really important, the two important identities are this one and this, okay, and this and also that one, okay. So maybe I should let me write. Let me write this. So Jn k of t. No, it's not J, it's F, I'm sorry. Fn k of t, the total force of infection is sum from j equals 1 to I n of 0 of lambda minus jk of t minus tau minus jk plus sum from j equals 1 to an k of t of lambda jk of t minus tau n jk. Okay, and then the next important formula is an k of t is pk of integral from 0 to t of epsilon n k of s ds. And the most important thing is the formula for epsilon k of t, which is s. Okay, let me write immediately Sn bar k of t, which means I've dividing by b and k means putting the bar above s times 1 over k sum over k prime of beta n k k prime f n k prime of t. By the way, maybe I should insist upon. Okay, so you see there are in a way there are two parameters which control or the evolution of the epidemic. There is a lambda, okay, which is random, which is associated to each individual, which is sort of typical of the illness, and there are those beta kk prime, which are more like describing the social contacts, the intensity of the social contacts. So, for instance, of course, the diagonal terms in this matrix are very important. They tell you about the local infection. Local infection are important. They don't need to be all equal. For instance, we could say they are all equal to 1, the diagonal terms. But I don't want to say that because those diagonal terms, they can, I mean, if you are in a patch which is essentially a desert, or in a patch which is New York City, of course, the density, intensity of contacts are very different. So maybe you want to have different betas. Okay. So this is really typical of the illness, the fact that the illness and the way each individual reacts to the illness. So he's more or less, and how long time has evolved since infection time, the age of infection. So this gives you, if you like, this tells you the probability when you meet someone, probability is to infect him. Okay, and that gives you the rate of contacts between the various patches and inside each patch.
one thing which is still a little funny is I assume eventually you want to send k to infinity.
Yes.
And then the diagonal term you could just as well erase from your equation because it would not be there.
I don't think so.
Well, 1 over k times beta k. K goes to 0 unless you beta k.
Yes.
Yes.
But you integrate
No, but
on
you're
the,
summing
you integrate
over
on
all
each
Ks.
interval. You integrate on the interval, and the length of the interval is k. So, okay, maybe we can rediscuss that when I show the final, the limiting equations. Okay.
Well, yeah, but you're summing them up, right? So even if they're solved, you have infinite percentages you're summing.
Okay, we will see the limiting model.
Are you assuming mass action instance or standard instance? Are you assuming mass action instance or standard instance for the infection? Divided by n or it's not?
Oh yes, I'm dividing by n. In fact, I don't divide by n. I divide by bn. Okay. So each quantity, whether this is f, s, I, r, when I divide by bn, then I put a bar on top of it. Okay. And where bn is this, bn of x is this guy. Okay.
Okay.
I mean, going from the k notation with k into the notation of with x is just summing over k and putting these indicators, which are missing on those two lines. I agree. Okay, now we wish to take the limit. Oops, m is missing. We wish to take the limit as n goes to infinity in this system and also in this guy. But I will first consider those. Okay. So the okay, maybe now let me state the main assumptions. So the first assumption is as k goes to infinity and n goes to infinity, the infimum over k of b and k goes to infinity, but I need to assume that the sup over those is finite. The sup of those ratios is finite, which means that they are of this, the population size are of the same order in the different locations. And essentially then this just means that then n goes to infinity faster than k. Okay. Next, we assume, of course, that the initial conditions converge towards appropriate limits, namely, okay, I'm always using in the x variable, I always use the L1 norm. Okay, so in L1 you assume that you have those convergences. Okay, I don't know. Those could be deterministic or random, the initial conditions, but whatever. If they are random, you need just to assume that they converge in probability. Now, next, I want the sup of those to be finite, and I want that. Okay, so beta n xx prime. Okay, there is a sort of confusion between notations, but okay, I hope you will allow me to do that. So beta n of xx prime is not exactly the sum over kk prime of beta n kk prime times those two indicators. But first of all, there is this renormalization by 1 over k. And next, I need to put the ratio here because, well, you will see the reason in a minute. Okay. Yes, the ratio is finite bounded, so it doesn't spoil the conversion, so it doesn't make the conversion more. Okay, and then concerning lambda, those lambdas, I assume that they are bounded almost surely by fixed constants. I'm not completely happy with this assumption. I would prefer to be able to bound those by some random variable which has some finite moment of some order, but that I'm not able to prove the convergence with. I would not be able to prove the convergence with those kind of assumptions, unfortunately. So there is this bound, and lambda has at most a given fixed number of jumps, and is uniformly continuous between its jumps. And then I use net notation. So the bar for most quantities is just division by b and k, but here the bar means expectation. Yes.
is joined.
Yes.
Does that mean that that sum there is zero? The two indicators multiply each other are zero for all combinations except one. There's only one x and x prime for which you have this.
Yes.
So it sort of just picks out, the sum just picks out which.
So, but you divide, so picking up of that, so it's only equal to, you only pick out one term.
Yes.
Beta kk prime is bounded, bn over bn is also bounded. 1 over k goes to infinity. So the L infinity norm of beta n of x prime goes to 0.
Yes. Yes, but once you integrate.
The integral is 0, 1, it's still going to be.
I think this is correct. And we have to, well,
Or maybe Tom, you're not right, because there are many, each cell contains.
yes.
So there's not just one.
I have to think about this. Your question disturbs me, but certainly the essential thing is that I want
Cases, there's only one case, but it's,
yeah, certainly I want this function to converge to a non-zero function in L1 or maybe stronger in infinity, whatever. And maybe I don't need exactly, maybe there is an error, maybe I don't need this assumption, but I need rather that the beta n is bounded. Okay, maybe I have to double check. I will double check. I'm sorry. Okay, so now, so the limiting quantities, limiting equation. Now, I consider this system of equations. And now in this system, there is a new notation, which is the distribution function of this variable eta, okay? And FC is one of those distribution functions. Okay, so S n bar of Tx is S bar 0 of Tx minus integral from 0 to T of psi epsilon bar of Sx ds. I'm sorry, the x is missing here, the variable x is missing. F bar of Tx is the contribution of the initially infected individuals, which is this, plus the contribution of the newly infected individuals, which is the integral of the T of lambda bar of T minus S epsilon bar S of Sx ds. Okay, here I have the x, but I'm sorry, here I'm missing the x, 2 errors. And then, okay, and then the rest is here. I have not written the I bar of Tx because the I bar of Tx is obtained from this by choosing A equals plus infinity. Okay, so this is the limit, the proportion of the density of individuals who at time t and location x have been infected for less than time a, and this is the density of removed individuals at time t and location x. But okay, what the main message is that the important thing is this system of two equations. Okay, so this is a system of equations with x is just a parameter. Those are integral equations. Okay, this is an ODE. For each x, this is an ODE, ordinary differential equation. This is an integral equation because you see here you have lambda bar of t minus s, so t is the same as this t. Okay, so it's not. This is not an ODE. Okay, this comes from the. I mean, as soon as you have you take the low large number limit of a non-Markovian epidemic model, you end up, you don't have limiting ODEs, you have integral equations or PDEs. If you put as a new variable the age of infection, you have a PDE. I will show you the PDE at the end of the talk. Okay. Where now the psi bar, the epsilon bar of Tx is this guy. S bar of Tx, integral from 0 to 1 of beta of xx prime, f bar of Tx prime dx prime. Okay. So and you see, not only this is an integral equation, but it's an integral equation where you have, I mean, the equations for different values of x are interconnected. Okay, I mean, they are, yes, well, they are coupled. Okay, there is a coupling for the various x's through this integral. Okay, so now the convergence result says that if you compare S bar n of t with S bar of t, F bar n of t with F bar of t, and the same with R, J, etc., those L1 norms converge in probability as n goes to infinity uniformly in T and A, where the limits are given by the unique solution of the above set of integral equations. In fact, it's one should rather say that we have a system of two equations. We have a two-dimensional integral equation, which is Z1. And once you have solved those equations, then you know S bar, F bar, you know epsilon bar, and then you compute explicitly those, then you compute those quantities. Those quantities are given, are expressed through the solution of the system of the two first equations. Okay. Yes.
Question on your uniformity. So in this setting, usually the infection dies only out at time t with infinity. But near time t infinity, you have very few infected people. So how comes that your law of large numbers uniformity?
Local uniformity. Oops, I'm sorry.
Oh, you mean for any compact interval?
Yes. I'm sorry, this is a misprint. Local uniformity. Sorry. No, I don't pretend. I don't claim that I have uniformity for OT Laplace. I don't claim it. This is only local uniformity. Okay. It's written correct. Local uniformity. So essentially, what you have to prove is that this goes to zero locally uniformity in probability. Okay. So now the main idea of the proof is the following. So I take the difference S bar n minus S bar, F bar n minus F bar. Now I write. So if you remember, so an of Tx was an integral, a time change Poisson integral. I mean, the integral, Poisson process time change by the integral of epsilon n of Sx. So in fact, this an of Tx is just the integral of that guy plus a martingale term. And that martingale term is easily shown to go to zero as n goes to infinity. Now, the other one is a little more tricky. The other one, so you have to compare the evolution of that difference, which is in the approximate model and the limiting model, how evolves the force of infection due to the initially infected individuals. Okay. This is not too hard, but it is some work there is some work here. And then in the F, you see, in the F again, again, you see the Fn was this. It's written here. So this you can write as an integral with respect to dAn. This is this increasing function, which jumps at those times. Okay. And because dAn is almost psi n bar ds plus, is psi n bar ds plus a martingale. The martingale term, which goes to 0 here, should go to 0 here also. I mean, it's a little, okay, there is a t minus s here, it's, but okay, you can do it. But also there is another correction, which is the fact that here I have lambda bar, and here I have the lambda. Okay, so you have to show that the sum of the difference of lambda and lambda bars goes to 0. Okay, so all those correction terms I put in this guy. And so essentially you have to show that this goes to 0. This is easy because the second moment is of order 1 over n. That's easy to show. That this goes to 0. It's a little more tricky. And also this goes to 0. And then all those conversions are in probability in L1 locally uniformly in T. Moreover, now once suppose we have done this. Suppose we have done this. We should know that this, okay, this goes to 0. This is just our assumption. Okay, the assumption says this. This goes to 0. We show it. These and these go to 0. We show it, and then next you have to use some estimate of those differences. And now the fact is that you look at the difference epsilon bar n minus epsilon of tx. So you have this quantity minus this. And now the thing is that you can show a priori estimates of the sup over n, t, and x. Okay, it's always t less than or equal to some capital T. N, t, and x, the sup of this, you have your a priori estimate of the sup. And also, that is in your stochastic model, you can show that this, for instance, this, of course, this is less than 1. This is obvious. Now, the fact that this is bounded comes from the fact that the betas are bounded, the lambda is bounded, etc. So it's not too hard to show this is bounded. And then you look at the limiting equation, and you show that the solution of the limiting equation also has a bound. I mean, not because it's a limit of the thing which we don't know yet, but from the equation you can show that a priori estimates even before knowing that there is a unique solution. This is another thing we have to show, that there is a unique solution, but this limiting system of limiting equation. But before you know that there is a unique solution, you say, okay, if I have a solution, then it satisfies certain bounds. Okay, this is usual techniques for studying some equations, PDEs, ODEs, etc., integral equations. And then once you have this, now you and then you have also the difference beta n minus beta goes to 0 in proper for proper topology. Then it's not too hard to show that that difference is bounded by constant times by something which goes to 0, which takes into account the difference beta n minus beta plus constant times the difference of those and plus constant times the difference of those two, and then you get estimate and you can show that the difference goes to 0. Okay, this is the main idea of the proof. Okay, so now I go to my PD model. Suppose now capital F, remember that capital F is a distribution function of the variable eta, the duration of the infected period. Suppose this is absolutely continuous with a density little f. Okay, it's not absolutely necessary, but okay, but it's better to assume this. And then I define the associated hazard function. Okay, here I have T, A, but okay. The associated hazard function, which is F divided by F, capital FC. So it's, okay, hazard function is well known in some branch of probability and statistics. Okay, it's the rate at which you get removed given that you have not been removed yet. Okay, essentially. Okay, so now assume that the initial condition, which gives you the limiting infection ages of the various individuals at time 0. Suppose this is absolutely continuous, and let's call little I of 0 ax to be the a derivative of that function, then for all TA and almost everywhere in X, this is absolutely continuous. And its derivative satisfies this linear PDE. So di bar dt plus di bar dA equals minus mu of a I bar. Okay. And with the initial condition, which is given, of course, this, and some strange looking boundary condition. Okay, so this gives you the value at the boundary A equals 0, which is this quantity. Okay, I have this A bar is because I have not said that, but we assume that the initially infected individuals, there is a maximum of age of infection of the initially infected individuals. Okay, so which is A bar. Okay, so this is the boundary condition. Now, the fact is that what one can show is that this PDE has a unique solution. You see, this is the first order PDE. So first order linear PDE is solved by characteristics. So of course, you see that this derivative means derivative in the directions parallel to the first diagonal. And so first of all, we have that the derivative of the S bar is minus I bar. Of course, those who get infected, they get infected at the time when they have infection H0. So this formula is quite natural. And the above PD is a unique solution given as follows. So I bar of TAX. So there are two different expressions depending upon whether A is larger than T or less than T. And for A larger than T, you have this fraction times I bar of 0 A minus TX. So this is in terms of the initial condition, A times T equals 0. And the other term is in terms of the boundary condition at A equals 0. Okay. And okay, it's the fact that this is satisfied does not tell you that you have a unique solution, but because you need to know the boundary value. But the fact is the boundary value is, it's not too hard to show that the boundary function is a unique solution of this integral equation. So the boundary value is solve an integral equation. You see that on the right hand side, you have only, okay, you have this data. This is initial value, which is a given data, and you have on the right the boundary value. Okay, so we have this equation.
Can you go back to the previous slide?
Sure.
Okay, I'm doing what we should have done the whole time, use the microphone for questions. So there's something which I'm sort of a little confused here, which is that I would have expected there should be some derivative with respect to X appearing somewhere. It almost looks as if the problem is just independent for all X and you have no interaction. So why don't you get a PDE involving X?
Because there is no movement in the X direction. If there were movement in the X direction, then I would have, of course, a PD operator in X. Okay. So for instance, if the individuals, okay, I have a parallel work where I consider movement as a Markov chain between the sites. In the limit, I have a diffusion, and then I would have the infinitesimal generator of PD operator. Okay, even in the previous equation, I would have a PD operator.
So it seems your beta only appears through your boundary condition and doesn't really involve your differential equations. So you have the initial condition and the boundary condition, and
yes,
beta of X and Y only appears in the boundary condition.
Yes, because you see the infection produces individuals of infection H0, and beta explains the infection, and the infection produces doesn't produce people of infection age 2 or 3 or 10 or 100. Okay, so I think it's quite natural, and it's correct that the only way where that those the only coupling between the various values of x, the only reason why this is not just an equation for any fixed x, you have an equation is through this integral in x prime.
Thank you. Quick question.
Sure.
So the first part of your talk, you arrived at the system of, I guess, equations that you wrote as integral equations, but then now you have this proposition saying that you have this PDE, right? And so, well, how do you get from one? Is it just one comes up from a forward argument and the other from a backward argument type thing, or how do you get from this to the PDE?
No, it's just that you see, you look at this quantity and you differentiate with respect to A. And the thing is that if at time 0, this is differentiable with respect to A, then when you look at this, you see that you can differentiate with respect to A, because A enters only the bounds of the integral. Okay. In fact, we have another paper with the same co-author where, we have written several papers on non-Markovian models that are, in particular, one on varying infectivity, which has appeared in Siam Journal of Applied Math last year. And we have a paper where, in those papers we get, there is no A, there's no X, of course, there is no A, and we get those equations. And, so we have integral equations, and somehow, but there is also in parallel literature where people introduce PDEs. And so we said, so there's another way of thinking of the same thing. You see here, you have the T minus S because you have, so we have to take into account what is, this is, so to speak, this is the infection age, and this is what happens at time T. This is a contribution, all contribution of past infection to the present force of infection, okay? But if you don't like integral equations, you can write a PDE, okay? However, what is funny is that somehow the way, maybe there is another way to do the same thing, but the way I understand that I can show existence uniqueness of this PDE is by writing an integral equation for the boundary condition, for the boundary function. Okay, so now references. So these are the past works with my co-authors. So this is the first paper where we had the functional limit theorem for non-Markovian epidemic models. This is the oldest paper, but it appeared only this year. We have a paper on where we use the models like this one for the estimate of the COVID epidemic in France. So here we have, this is the first paper where we study epidemic models with varying infectivity. So with this kind of lambda, appeared last year. And here, this is a paper where there is a multi-patch, multi-group epidemic model with varying infectivity, but there is no, the number of patches fixed, doesn't go to infinity like in what I presented today, okay? So that paper is going to appear at the end of this year. And then, so somehow, first of all, this is a very important paper, which is quoted many, many times, mostly by people who we use only the one particular case of their model with fixed, with fixed rates, okay? And in fact, in that paper, the idea of varying infectivity was already there, not as random varying infectivity, but varying infectivity, okay? And by the way, there is the next two papers by the same authors, Kamak and McKendrick, 32, 33, they consider also varying susceptibility or immunity, and that we have done also very recently. Okay, and then there are those papers, Dickman, Kendall, and Sim, which consider spatial spread of epidemic and PDEs, which are sort of similar to what we do, except, well, Kendall, Kendall is for Markovian models, so it's different. Probably Dickman and Sim is closer to what we do. Okay, thank you.
Okay. Thank you very much. More questions?
So what was the role of your function lambda?
What was the role of your function lambda?
Well, the function lambda,
Where does it show up? Or
it
does
shows up in the force of
Oh, yeah,
infectivity.
I see. This is the part of the force of infection. And this
Force
is,
of infection, and the force of infection is essentially in the rate of propagation of the epidemic.
I see. So you can think of it as some kind of load of the virus over the time of infectiousness, right?
That's all.
Okay.
Other questions? So let me just ask, while it's more common. So to some extent, what you have shown is that in this patch model, sort of mean field is exact, right?
Yes. Yes. Well, similarly, what is interesting, in the paper, this Siam paper, we sort of recover exactly the equation of Kermack and McKendrick from stochastic models. Okay, it's low large number limit of a stochastic model.
No, it's sort of have an interesting comment with is that the two of us were discussing and were sort of looking at this old model, and we were saying somebody should prove that actually it's a stochastic limit, and then sort of 2 days later we actually found one of your papers. And that was, but you got invited to this long before we had read this paper, so somehow it was a lucky accident. Now at least he and I can learn a little of the details, so this was very nice.
Yes.
So you said you assumed that lambda was bounded. I don't have a problem with that at all. But then did you make any assumptions about eta, the duration of the infectious period? I don't have any problem with saying that lambda is bounded. That's perfectly fine for me. But did you also make some assumption about eta being
Not really.
bounded or bounded in probability, or?
I don't think I need anything like that.
Why do you define eta then?
Excuse me?
Why do you even define eta if you don't make any assumptions about it?
Oh, because when I want to why do I define the eta? Because because in order to describe, oops, maybe it was here. It's when I want to write the equations for here. When I want the equations for I n r n, then I need those quantities. Okay.
It also appears in the next page. You need the distribution function.
Yes. Here, for the same reason, in the limit, you need not the variable on the variables, but the distribution function. Or that one, the variable. It enters the limiting equations.
You need no assumption of the distribution function.
I mean, for instance,
well, except
if it goes up to 1 and then it decays exponentially forever, then eta is always positive. I'm sure that your results are still valid.
Yeah, I think so. Just there is no, then of course, then R bar of Tx is just R bar 0 of Tx.
Then I had one more question. Let's see if I remember it. So one thing is your model. I would say your model is that you have a process lambda of t, which is a stochastic process.
Yes.
That is sort of given to you.
Yes.
And then the other part of the model is this matrix beta.
Yes.
But then my question was, so you assume that the contact rate between all of these patches are of the same order. So I think in your model, you don't allow to have a much higher rate of contacts within your own group. You cannot sort of have a contact rate of a different order on the diagonal. I don't think you allow for
Different
that.
order, you mean in terms of N, capital N?
I mean, suppose you half of your contacts are within your own patch and the other half is with the rest of the population. I don't think it applies to them.
That's not a problem. As long as it's something given which doesn't depend upon N, you can have a very different value.
No, but you had this supremum of a ratio was bounded.
No, but that was different. Nothing to do. The supremum which was bounded. Okay, it's here. Where is it? It's here. It's not. This has nothing to do with beta. This is the number of individuals in each patch. Okay, so the ratios as n goes to infinity, those ratios should not explode. None of these ratios may explode.
So you mean that your limiting function beta could be 0 except on the diagonal?
Okay, that I have to think about.
I was just wondering, because in some situations you have sort of a much higher rate on the diagonal and a lower. So it was more like a question, is that covered in your model or not?
I guess so, but how far is it covered? I have to double check.
Okay, thank you very much.
We just finished that paper a short time ago, so.
So I have a follow-up question on that. Your beta, so your beta of x and x prime converges in L1, but given that your beta n k k prime is bounded, it will probably converge to a bounded function, right? So could you deal with a beta which is not a bounded function, but which has some 1 over x minus x prime to some power?
Probably it's not covered by what we have done so far, but I don't know whether we can go further than what we've done. And, yes, okay. It's a good question, but we have more thought of, so far we have thought of situations of beta as bounded. I agree.
More question. Okay.
This is kind of similar to a question I tried to ask earlier, and just because we're talking about the beta still. So I think that earlier in the model, like in the F and the A rates, they're very similar to sort of the Kermack-McKendrick, like beta times S times I based on the dynamics, right? So it's just a little more complicated because the lambdas are not constant. So that I kind of understand as like SIR interaction dynamics. But then the betas between patches are kind of just like, there's new flow and it just starts as brand new infections, but it doesn't really come from interactions. It kind of just comes from nowhere, right? It's like a new infection rate. So
of course, you could have. You mean you could have at the initial time some patches could be free of infectious individuals, no epidemic in some of the patches, and then you have immigration. I mean, then you have the epidemic coming from outside. Of course, this is allowed by in this model.
Yeah,
that's what you mean.
Yes. Yeah, I probably should just ask you offline. Yeah, I'm just trying to understand why we don't need beta to appear in any kind of instantaneous rates other than a boundary condition. But I'll ask you.
So maybe. Okay, you call it spatial patches, but I could also exit between 0 and 1. Okay, so I could think of 0 as I'm born today and 1 is 100 years old. And these just are age groups, and you have different rates on infections between different ages because the 0-old ones drives 100-year-olds nuts, so they never see each other. And there's sort of a function of the age difference which would create contact. So I could just think of that as an inhomogeneous model where I have a continuous number of groups, right? I don't have to think of them as patches in space.
Of course.
And then maybe that answers your question.
Of course, in a sense, that could be thought of as Graphon model, which is not really space.
I have an epidemiological question.
Okay, so you get to close the English question because we all want some cookies and they're served at,
Cookies.
oh no, we have until 3, right?
No, what?
The next talk is at 3, I guess.
The next talk is 3, so we have missed all the food, but that's fine.
I'll ask you later. Don't worry.
No, you're sure?
Cookies are more important.
Cookies are gone anyhow. So. Okay, see you back at 3.
Yeah.